Welcome to This Explainer. Today we're diving into something that sounds straight out of a sci-fi movie. We're going to unpack the impossible-sounding physics of how quantum computers might, actually literally, be calculating our toughest problems across parallel universes. I know it sounds crazy, but we're going to look at the very real physics and the groundbreaking hardware that suggest our universe is just one of many.
So let's start here. 10 septillion. That is a 1 followed by 24 zeros. To put that massive number into perspective, that is almost a quintillion times older than the 13.8 billion year lifespan of our entire universe. It's a completely unfathomable amount of time. And yet Google's new Willow quantum chip just solved a complex math problem, the random circuit sampling benchmark, that would take a classical supercomputer 10 septillion years to figure out. And the Willow chip? It knocked it out in under 5 minutes. How on earth is a machine sitting in our physical reality capable of doing that?
Section 1. The Quantum Computing Leap.
To really grasp how this reality-breaking speed is even possible, we have to look at the fundamental difference between classical and quantum computing. Classical computers, like the laptop or phone you're using right now, they process ones and zeros sequentially, one after the other. But quantum computers play by completely different rules. They use qubits. Thanks to a quantum property called superposition, these qubits can exist as a 1, a 0, or both at the exact same time. This is a real game changer. Because instead of trying one path, hitting a dead end, and then going back to try another one by one, a quantum computer explores multiple possible pathways simultaneously. And this perfectly illustrates a massive problem of scale. A tiny 50-qubit system already needs about 1 petabyte of classical memory just to simulate it. But watch what happens when you scale up. By the time you reach just 300 qubits, you would need more classical bits to represent those states than there are atoms in the entire observable universe. Let that sink in. No classical supercomputer could ever hold that much memory. This impossible memory deficit led pioneering physicist David Deutsch to pose a really famous, reality-bending question. He basically asked, if a quantum computer solves a problem that requires more resources than physically exist in our entire universe, where exactly is the computer getting its power from? If there literally aren't enough atoms in our universe to do the math, where is the math actually happening?
Which brings us to Section 2, the Many Worlds Interpretation.
Tracing this idea chronologically is fascinating because we get to see how a hugely controversial thesis became the foundation for modern tech. Back in 1957, Hugh Everett proposed the Many Worlds thesis. He suggested that the universe actually branches to realize every possible quantum outcome. For decades, it was mostly brushed off. But then, in the 1980s, David Deutsch used that exact framework to develop the theory of quantum computing. Fast forward to 2019. Google's Sycamore chip hit a 200-second benchmark that would have taken classical computers 10,000 years. And today, Google's Willow has completely shattered that record, validating the insane exponential growth that these quantum theories predicted.
So let's unpack the core mechanism of many worlds, because it completely flips how we view reality. The traditional view, the Copenhagen interpretation, says particles exist in this fuzzy probability cloud until they're measured, and then they randomly collapse into a single state. But the many worlds theory argues that the math, specifically the Schrödinger equation, never actually shows a collapse. Instead, every single possible outcome of a quantum event actually happens. The universe just splits, or branches. The only reason you just see one outcome is because the version of you making the measurement split as well, into a newly branched parallel universe.
Section 3. Evidence from the shadows. Now, you might be thinking, okay, but if these infinite other universes exist, how do we even know they're there? Well, the famous double-slit experiment gives us a stunning clue. When you fire single photons, individual particles of light, at a barrier with 2 slits, they don't just form 2 lines on the wall. They create an interference pattern of bright and dark bands, as if a single particle went through both slits and interfered with itself like a wave. But here's the wild part. When researchers cut 2 more slits, making it 4 total, you get unexpected dark spots precisely where you'd expect the light to be the brightest. By adding more light, a spot actually went dark.
Professor Deutsch explains this bizarre interference by defining what he calls shadow particles. These are actual, real particles of matter and energy from a parallel universe. We can't see them with our eyes, and our instruments can't detect them directly, but they share a quantum space with our universe's particles. So when that photon passes through the 4-slit setup, it's actually being pushed aside and deflected by unseen shadow photons arriving from parallel universes. They bump into our universe strictly through this phenomenon of quantum interference.
Now, if there are entire worlds of shadow particles all around us,
why don't we experience these split realities in our everyday lives? The culprit here is quantum decoherence. Basically, this is a one-way street where the incredibly delicate quantum state, that weirdness of being in multiple states at once, quickly leaks out into the macroscopic environment. The second a quantum system gets tangled up with its messy surroundings, the universes stop interfering with each other. They become completely, irreversibly separated branches.
Section 4. Computing across parallel universes.
So the big question is, how does a machine like Google's Willow harness this unseen multiverse without instantly falling victim to that decoherence? It relies on a very precise 5-step process. First, scientists painstakingly isolate the qubits, cooling them down to near absolute zero just to block out environmental noise. Second, they push those qubits into quantum superposition. Third, as the algorithm runs, the computation literally branches out across millions of parallel universes, calculating every possibility at once. Fourth, and this is the absolute magic of it, the computer uses that exact same quantum interference we saw in the slit experiment to cancel out all the wrong answers from the other universes. And finally, step 5, the one correct solution is to deposit it right back here in our single, tangible reality.
Section 5. Redefining our reality.
Using the multiverse to calculate a 10 septillion-year math problem in 5 minutes, it forces us to ask some really profound personal questions about our own existence. Because, as theoretical physicist Sean Carroll points out, we can't just draw some arbitrary line between the weird quantum world and our everyday world. Human beings are fundamentally made of atoms, right? Electrons, protons, neutrons. And because those atoms follow these exact same quantum rules, it mathematically implies that we too are fundamentally part of this endlessly branching reality.
According to Deutsch, this isn't just some abstract math concept. There are actual parallel versions of you. Whenever a quantum choice is made, the universe splits. The versions of you in these newly split universes are completely, 100% identical up until the exact microsecond a different quantum event happens. And from that moment on, they split off like identical twins, evolving separately but simultaneously across a massive expanding multiverse.
This completely reshapes that centuries-old debate between free will and determinism. The many worlds interpretation offers a really fascinating look at reality. On one hand, determinism totally rules the multiverse as a whole. The math ensures that everything that physically can happen does happen in separate branches. Somewhere out there, there's a branch where you made every possible choice. But on the other hand, many physicists argue that free will is still preserved within your specific branch. Why? Because your subjective experience is only tied to the reality you are actively navigating. The choices you make right now still dictate which branch of reality you will consciously experience tomorrow.
The physics behind quantum computing isn't just theoretical chalk on a blackboard anymore. Machines like Google's Willow are proving that accessing this kind of unimaginable computational power requires tapping into resources far beyond our own isolated universe. So, as we wrap up this explainer, I want to leave you with a thought to really ponder today. If every single decision, every quantum event creates a brand new reality where a different outcome plays out, what does that mean for the specific version of you making choices right at this exact moment?